Okay, I've been re-looking at chapter 7, and I just added a second homework assignment because there's so much stuff in chapters, and it's so huge. It's so huge. It's such a big ending. Um, um, the conservation of momentum and all of these things, and also the other thing that I was center of mass shows up. You know how to find the center of mass of something, and it's very important in everything we do in physics and in physical therapy and all these things that healthcare professionals in the health, as I call them, and so still every piece of equipment you use, applies conservation of momentum type thing. So I added an extra assignment, and I'm going to give this all in a summary, and then you work a couple problems in class. And so this probably means this chapter to Tuesday which is fun, which is fun. Okay, so without further ado, let's take a look at now. This is a hard problem. This one's tricky. Have fun, but I want you to have fun with it. It's physics. Damn it, have fun. So, um, again, you base right now. All we're looking at is the conservation momentum, and this one now is going in 2 dimensions. The momentum before is equal to the momentum after. And what we're going to do in class is I've already got a few problems outlined that I'm going to do in class. I kind of said this one. I guess I'll do problem 31 then, or 40 in class tomorrow. All right, so I guess we'll set up this one. And this one might take one or two of these little videos because I don't like them to go much longer than 4 minutes. Oh, I need to go to the student view. You already saw the answer. Okay, so here we go. So let's look at problem 34. All we're doing, I'm telling you, one, don't plug in numbers until you're completely done, because these numbers are crazy and you're going to have issues with it. All right, you're going to have issues. Basically, what's going on here is we've got this small puck coming in that has a very small mass. It's hitting another puck that has twice its mass in this case. So that's kind of nice. We could probably use that in some way. The collision is not head on, and so they glance off of each other. First of all, there are 2 kinds of collisions. Okay, I want to talk about that real quick. 2 kinds of collisions, and I'll talk about this tomorrow in class. Collisions. There's elastic and inelastic, and in between. Neither elastic or inelastic. I before E except after C. Except for in this case. That just looks funny to me. Is that the way you spell neither? Oh, man. Yeah. All right. Anyway, now I feel like an idiot because I don't know if that's right. And then, that's where, like, coefficients of restitution, which we do in physics of sport, where we drop something and it bounces back up. Drop a basketball from a certain height, and it bounces, supposed to bounce up to a certain height. But it doesn't come back up to the height that you dropped it. Obviously, it lost a lot of energy, and that's a collision that's not elastic and not inelastic. Because if it's an elastic collision, here's the big idea, and then I'll stop. An elastic collision means this: the kinetic energy before is equal to the kinetic energy after the collision. So if I drop something, bang, hits the ground. V1 equals 10 meters per second. In this case, negative, but since it's kinetic energy, we're going to square that. And then, boom, it shoots back up after the collision. The final is equal to positive 10 meters per second the mass stayed the same. The kinetic energy before is equal to the kinetic energy after. That's an elastic collision. Inelastic collision, smoosh, you stick together. Classic inelastic collision. Boy, I'm having trouble writing. You know what my problem is today? It was pouring down rain this morning and I didn't get a chance to go run. Inelastic collision, the kinetic energy after is less than the kinetic energy before. In other words, it would bounce down. That happens. And that's also in when it's neither. But here's the thing. An inelastic collision means they stick together. Classic example. Here's a sled. All right. Here's a little sled sitting here, waiting for this kid to come jump on it. Kid comes running along. He's going to jump on the sled. Boom. He's got a mass 1. This sled has a mass 2. He's got a velocity of 10 meters per second. Fast kid. All right, 10 meters per second. He jumps on the sled. So the momentum before is equal to the momentum afterwards, but now the momentums are the same. And the momentums are the same. The momentums equal each other, but you might lose some energy. All right, so here's what happens. So then you've got m1 times 10 plus m2 times 0 is equal to m1 plus m2 when he jumps on the sled times some final velocity. Those are kind of nice and fun to solve. All right, so he jumps on the sled, boom. So the kid is on the sled now, okay, going at 6 meters per second. You better not be going faster than that, because if he's going faster than that, he's got some kind of momentum's not conserved, and momentum will not be conserved if an external force is acting on it. Okay, so there's your definitions of elastic and inelastic. Now we're ready to look at this problem.